Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 12th physics, magnetism and matter, chapter 5 NCERT solution part 2. Our mission is to provide free classes on YouTube for all the students of class 6 to class 12 and also for the students who are preparing for IIT, JEE, NEET, NDA and other competitive examinations. Before we begin, we have a small request. Please subscribe, like and share our channel, and please click on the subscribe button to support us, and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Let us begin today's lesson. First question is question number 5.5. A closely wound solenoid of 800 turns and area of cross section 2.5 multiplied by 10 to the power minus 4 meters square carries a current of 3 ampere. Explain the sense in which the solenoid acts like a bar magnet. What is its associated magnetic moment? Let us see the solution. The solution is number of turns in the solenoid n is equal to 800. Area of cross section A is equal to 2.5 multiplied by 10 to the power minus 4 meter square, which is given in the question. Current in the solenoid I is equal to 3 ampere, which is also given in the question. A current carrying solenoid behaves as a bar magnet because a magnetic field develops along its axis, that is, along its length. The magnetic moment associated with the given current carrying solenoid is calculated as M is equal to NIA, that is equal to 800 multiplied by 3 multiplied by 2.5 multiplied by 10 to the power minus 4 is equal to 0.6 joule per T. Let us see question number 5.6. If the solenoid in exercise 5.5 is free to turn about the vertical direction and a uniform horizontal magnetic field of 0.25 Tesla is applied, what is the magnitude of the torque on the solenoid when its axis makes an angle of 30 degrees with the direction of the applied field? Let us see the solution. So solution of 5.6. Magnetic field strength B is given as B is equal to 0.25 T. Magnetic moment M is equal to 0.6 T inverse. The angle theta between the axis of the solenoid and the direction of the applied field is 30 degrees. Therefore, the torque acting on the solenoid is given as tau is equal to mb sine theta. Putting the value of m, b and theta, we get 0.6 multiplied by 0.25 sine 30 degree. Upon solving, we get 7.5 multiplied by 10 to the power minus 2 joule. Let us see the next question. Next question is 5.7. A bar magnet of magnetic moment 1.5 joule per Tesla lies align with the direction of a uniform magnetic field 0.22 Tesla. A. What is the amount of work required by the external torque to turn the magnet so as to align its magnetic moment? 1. Normal to the field direction, 2. Opposite to the field direction. B. What is the torque on the magnet in case 1 and case 2? So there are many questions asked in a single question. Let us see the solution of each of them. Magnetic moment M is equal to 1.5 Joule per Tesla. Magnetic field strength P is equal to 0.22 Tesla. 1. Initial angle between the axis and the magnetic field theta 1 is equal to 0. Final angle between the axis and the magnetic field theta 2 is equal to 90 degree. The work required to make the magnetic moment normal to the direction of the magnetic field is given as W is equal to minus mb cos theta 2 minus theta 1, which is equal to putting the values of mb cos mb theta 2 and theta 1, we get minus 1.5 multiplied by 0.22 theta 2 is equal to 90 degree and theta 1 is equal to 0 degree. We get minus 0.33 bracket 0 minus 1, which is equal to 0.33 joule. The next part of the question is the solution to the next part of the question. A is initial angle between the axis and the magnetic field theta 1 is equal to 0. Final angle between the axis and magnetic field theta 2 is equal to 180 degree. The work done to make the magnetic moment opposite to the direction of the magnetic field is given as W is equal to minus mb cos theta 2 minus cos theta 1. Putting the value of mb theta 2 and theta 1, we get 1.5 multiplied by 0.22 multiplied by cos bracket cos 180 degree minus cos 0 degree, which is equal to minus 0.33 under bracket minus 1 minus 1, and upon solving we get 0.66 joule. Now let us see the B part of the question. In case 1, theta is equal to theta 2, that is equal to 90 degree. Torque tau is equal to mb sine theta. Putting the value of mb and theta, we get 1.5 multiplied by 0.22 multiplied by sine 90 degree, which is upon solving we get 0.33 joule. In case 2, theta is equal to theta 2 is equal to 180 degree. Torque tau is equal to mb sine theta. Putting the value of mb and theta, we get 0 degree, 0 joule. Let us see the next problem. The next question is 5.8. A closely owned solenoid of 2000 turns, an area of cross section 1.6 multiplied by 10 to the power minus 4 meters square carry a current of 4 ampere is suspended through its center, allowing it to turn in a horizontal plane. What is the magnetic moment associated with the solenoid? B. What is the force and torque on the solenoid if a uniform horizontal magnetic field of 7.5 multiplied by 10 to the power minus 2 Tesla is set up at an angle of 30 degree with the axis of the solenoid? Let us see the solution. So here we have number of turns on the solenoid, that is n is equal to 2000. area of cross section of the solenoid A is equal to 1.6 10 to the power minus 2 meters square. Current on the solenoid I is equal to 4 ampere. A, the magnetic moment along the axis of the solenoid is calculated as NAI, putting the value of N, A and I as 2000 multiplied by 1.6 10 to the power minus 4 multiplied by 4, which is equal to 1.28 ampere meter square. Let us see the next part of the solution. The next part of the solution, part B, magnetic field B is equal to 7.5 multiplied by 10 to the power minus 2 Tesla, angle between the magnetic field and the axis of the solenoid, theta is equal to 30 degree, torque tau is equal to mb sine theta, putting the value of m, b and theta, we get 1.28 multiplied by 7.5 multiplied by 10 to the power minus 2 multiplied by sine 30 degree, which is equal to 4.8 multiplied by 10 to the power minus 2 Newton meter. Since the magnetic field is uniform and the force on the solenoid is 0, the torque on the solenoid is 4.8 multiplied by 10 to the power 7 Newton meter. Let us see the next problem. Now, problem number 5.9. A circular coil of 16 turns and radius 10 cm carrying a current of 0.75 A ampere rests with its plane normal to an external field of magnitude 5 into 10 to the power minus 2 meter at 10 to the minus 2 Tesla. The coil is free to turn about an axis in its plane perpendicular to the field direction. When the coil is turned slightly and released, it oscillates about its stable equilibrium with the frequency of 2 per second. What is the moment of inertia of the coil about its axis of rotation? Let us see the solution. Number of turns in the coil, in the circular coil, n is equal to 16. Radius of the coil r is equal to 10 centimeter, which is equal to 0.1 meter. Cross section of the coil A is equal to n r square, that is n multiplied by 0.1 square meter square. Current in the coil I is equal to 0.75 ampere. Magnetic field strength B is equal to 5 multiplied by 10 to the minus 2 Tesla. Frequency of oscillation of the coil nu is equal to 2.0 per second. Magnetic moment M is equal to NIA, that is equal to NI, instead of A we can write pi r square. Putting the value of N, I, pi and r, we get 16 multiplied by 0.75 multiplied by n multiplied by 0.1 square. Putting the value of and solving it, we get, instead of n we can write 16. So now upon solving we get 0.377 J per T or Tesla, joule per Tesla. Frequency is given by the relation nu is equal to 1 by 2 pi under root mb upon I, where I is the moment of inertia of the coil. So putting the value so calculating the value with respect to I, that is I is equal to mb upon 4 pi square nu square. Putting the value of mb, pi and nu, we get 0.377 multiplied by 5 into 10 to the minus 2 upon 4 pi square multiplied by 2 square. Upon solving we get 1.19 multiplied by 10 to the power minus 4 kilogram meter square. Hence, the moment of inertia of the coil about its axis of rotation is 1.19 multiplied by 10 to the minus 4 kilogram meter square. Now let us see the next problem. Question number 5.10. A magnetic needle free to rotate in a vertical plane parallel to the magnetic meridian has its north pole north up pointing down at 22° with the horizontal. The horizontal component of the Earth's magnetic field at the place is known to be 0.35 G. Determine the magnitude of the Earth's magnetic field at that place. So let us see the solution. So solution for 5.10. Horizontal component of Earth's magnetic field pH is equal to 0.35 G. Angle made by the needle with the horizontal plane, angle of dip delta is equal to 22°. Earth's magnetic field strength B is equal to B. We can relate B and BH as BH is equal to B cos theta. Therefore, B is equal to BH cos delta, where the angle is delta. Now, now putting the value of BH and delta, we get 0.35 upon cos 22°, which is upon solving we get 0.377 G. Hence, the strength of the Earth's magnetic field at a given location is 0.377 G. Now, let us see the next question. The next question is 5.11. At a certain location in Africa, a compass point 12° west of the geographic north. The north tie-up of magnetic needle of a deep circle placed in a plane of magnetic meridian point 60° above the horizontal. The horizontal component of the Earth's field is measured to be 0.16 G. Specify the direction and magnitude of Earth's magnetic field at the location. Let us see the solution. Angle of declination theta is equal to 12°. Angle of dip delta is equal to 60°. Horizontal component of Earth's magnetic field BH is equal to 0.16 G. Earth's magnetic field at a given location is equal to B. We can relate B and BH as BH is equal to cos delta, B is equal to BH upon cos delta. Putting the value of BH and delta, we get 0.16 upon cos 60°, which is equal to 0.32 G. Therefore, Earth's magnetic field lies in the vertical plane 12° west of the geographic meridian, making an angle 60° upward with the horizontal direction. Its magnitude is 0.32 G. Next question, 5.12. A short bar magnet has a magnetic moment of 0.48 Joule per Tesla. Give the direction and magnitude of the magnetic field produced by the magnet at a distance of 10 cm from the center of the magnet on A, the axis, B, the equatorial line, normal bisector of the magnet. Let us see the solution. So, the solution to 5.12 is magnetic moment of a bar magnet M is equal to 0.48 Joule per Tesla. A, distance D is equal to 10 cm, that is 0.1 meter. Magnetic field at distance D from the center of the magnet on the axis is given by the relation B is equal to mu naught by 4 pi multiplied by 2m by dq, where mu naught is equal to permittivity of a free space. Its value is equal to 4 pi 10 to the power minus 7 T m A inverse. So putting the values, we get B is equal to 4 pi multiplied by 10 to the power minus 7 multiplied by 2 multiplied by 0.48 upon 4 pi multiplied by zero point 0.1 whole cube. Upon solving, we get 0.96 multiplied by 10 to the power minus 4 Tesla, which is equal to 0.96 G. The magnetic field is along the south and north direction. Let us see the part B solution. So the magnetic field at a distance of 10 centimeter, that is d is equal to 0.1 meter on the equatorial line of the magnet, is given as B is equal to mu naught multiplied by m upon 4 pi multiplied by dq. Putting the value of mu naught, m, pi and d, we get 4 pi multiplied by 10 to the power minus 7 multiplied by 0.48 upon zero point 0.1 4 pi multiplied by zero point 0.1 whole cube. That upon solving, we get 0.48 G. The magnetic field is along the north-south direction. Let us see the next question. We'll see rest of the question in the next session. Before closing our session, today's session, we request you to subscribe, like and share our YouTube channel among your friends and relatives. Please click on the subscribe button to support us and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for watching our videos and supporting us. Thank you very much.